Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Okay, so hi everyone. Let me check that whether I am audible or not. Or can someone please just confirm that my voice is clear or not? Okay. Okay, so everything seems good to me. So hi everyone. This side Ayush Anand Tripathi, our DSM mentor and problem setter at Geeks for Geeks, and I welcome you all to this post analysis of last problem of the day, which was named as find the closest element in BST. So let me just first share my screen. Okay, hi Kishan, hi Rishit. So the problem was named as find the closest element in BST, and in this problem we have been given a binary search tree and an integer k, and our task is to find the least absolute difference between any node value of the BST and the given integer k. And if we take this example, then here this is our binary search tree and the value of k is 13. So the minimum possible absolute difference is 2, which is with this node 11. The absolute difference between k, which is 13, and 11 is 2, which is minimum possible. So is the problem statement clear to everyone? So is the problem statement is clear to everyone? Okay, thanks Shit. Please tell any tips for trees and graph traversal methods. Okay, so what you can do if you are looking for some free traverser, then you can check out some YouTube playlist. There are multiple YouTube playlists are there for graph and trees. But what I would suggest ki while learning the thing, start practicing the questions by your own, and don't forget to give the contest because that is the only way where you can learn a lot. Okay, so yes sir, yes sir. Okay, so now let's just see how we can solve this problem. So the brute force solution is straightforward. That is, we visit every node and we find the minimum possible absolute difference with k. So in brute force solution, we every node, visit every node and find the minimum possible absolute difference. Then what would be the time complexity? So then the time complexity is O of n, where n is the number of node you are visiting each and every node. But the expected time complexity is O of h only. So this is not the expected time complexity. We have to do something better. So is the brute force solution clear to everyone? Okay. So to solve this problem efficiently, you only need to recall the properties of a binary search tree, because here the given tree is a binary search tree. So just recall the properties of a binary search tree. And what are the properties of binary search tree? So in binary search tree, for every node, the node in its left subtree having value less than the node value, and this is the current node that I am talking about, and the node in its right subtree having value greater than node value. So let me write over here less than node value, and the node in its right subtree having value greater than node value. And in binary search tree, there is no concept of the duplicate element. So generally, we assume that there is no duplicate element in binary in the tree. So tell me, guys, did previously we exploit this property of binary search tree? That in the brute force solution, we are not using this property. That is, if the tree is not a binary search tree, then the complexity of a brute force solution is same. All right. So is this thing clear to everyone? That we didn't use the property of a binary search tree in our brute force solution. Okay. All right. So for every node, now in the efficient solution, for every node, we either move to its left subtree or to its right subtree. And when we move to its left subtree and when we move to its right subtree, so if the node value is greater than, please summarize in brief. Okay, okay, Piyush, just bear with me for next 2 minutes, and definitely we dry run on the first example. So if the node value is greater than k, then we only move to its right subtree, because we know that. So let me just draw this number line. So if this was the node value, and somewhere here we have k. So currently we are at our node value, and we know that all the nodes having value less than the node value is in its left subtree, and all the nodes having value greater than the node value in its right subtree. And we want to minimize the absolute difference, or we can say we want to find the closest node to the k. So that node definitely lie in the left subtree of the current node. So why we visit this right subtree? Because this will always increase your answer, that is, this will always increase the absolute difference. So we only make a call for its left subtree. All right. So is this thing clear to everyone? That is, if the node value is greater than k, then we call the recursive function for its left subtree. And similarly, if the node value is greater than is less than k. Okay, sorry, but here it should be less than k. Okay, I guess yes. So if the node value is less than k, That means in my number line, the k is lie in the right side of node value, somewhere here. And we know all the nodes having value greater than the node value is in the right subtree of node. So visiting its left subtree will only increase the absolute difference. So why we visit its left subtree? So we only make a call for its right subtree. Right subtree. All right. So is this thing clear to everyone? Okay. Thanks, Piyush. And here we have one base case, and we have one edge case. And the edge case was that there might be a case when the larger value is very large. So what I mean by this, so let's say the value of a k is greater than the node value. That means we visit its right subtree. But there might be a case when the the node value in its right subtree having value much greater than k. So let's say this was the node in the right subtree. So we want to minimize the absolute difference. So there might be a case when this difference is your minimum absolute difference. So we also consider this difference, that is absolute difference. So that is a absolute difference between node dot value minus k, because there might be a case when the node in its right subtree are very large. In that case, this difference can be greater than this difference. Or let me write some alphabets over here. So let's say this was d1 and this was d2. So there might be a case when d2 is greater than d1. That is the difference between k and x1 and the difference between node value and k. So we have to also consider this case, that is the difference between k and node value. So this was all about the explanation and observation. Now let's just see how we implement the solution. Or in case if you have any question, then feel free to write it in the chat. Or you guys are ready to move forward. Okay, so I guess now let's just see how we implement this solution. So instead of writing a separate recursive function, we can use this given function as well. And what would be our base case? So I'm not going to check that whether its left child exists or not. So rather than that, I write a separate recursive. Okay, I will write the separate base case for that. That is, if root is equal to null, then I will return some very large value, that is int max. And why I am returning int max? Because there is no node over here, so we cannot find the absolute difference. So we simply return int max. Is this base case is clear to everyone? Okay, thanks Mohit. All right, then what are the possible cases we have? The very first possible case that we have, when when the root data, that is the node value, is equal to k. In that case, I will simply return 0. That is the absolute difference between k and k is 0. So if root dot data is equal to k, then in that case I will simply return 0. Otherwise, we have two possible options. That is, we either visit its left subtree or we visit its right subtree. And when we visit its left subtree, so we visit its left subtree when the node value is greater than k. So I will simply check if root data is greater than k, then I will simply call the recursive function for its left subtree, that is minimum diff root dot left root left comma k. Okay, clear? Yes, yes. Okay, but here I forget one thing. That is, there might be a case when in the left subtree of the current node, when the node in the left subtree of the current node having value very small, such that their difference is greater than the current difference. So what I mean by this, let me explain you this with an example. So let me just first erase these things. So on a number line, let's say this. Okay, so yes, this is the node value, that is the current node, or we can say root, and this is our integer k, that is integer k is less than root, and we know this integer k is less than root, so we only visit its left subtree, and let's say in its left subtree there is only one node for which the value of node is x1, and this absolute difference is d1, and this absolute difference is d2. So there might be a case when the value of x1 is very small, such that d1 is greater than d2. So we also consider these two, this root node as well with k. So is this thing clear to everyone, that here we have to add one more condition when we consider root node? Okay, so here what I will return, I will simply return the minimum of absolute difference of current node, that is root data minus k, comma the value written by its left subtree, which is nothing but minimum difference with root left comma k. And similarly, the other case that we have, when the root data is less than k, in that case we only have to visit its right subtree. So I will simply return minimum of so let me just copy this thing, minimum of absolute difference between current root and k minus the value written by its right subtree. So here instead of left we have to write right, and then I will simply return that thing. So now let's just try to dry run. Let's just try to compile this. Okay, we got some error. Okay, thanks, Rishit. Okay, line number 47. This one. Okay, seems good. Now let's just try to submit this. Okay, accepted. And what is the time complexity now? Can anyone want to guess the time complexity? Okay, so the time complexity now is O of h. O of, yes, Rishit, O of h, where h is the height of BST. All right, because we are either visiting its left subtree or its right subtree. We are not calling the function for both the subtrees. That is, we either visit its left subtree or right subtree. So in the worst case, the time complexity is height of a binary search tree. So this was all about the explanation and observation. I hope this makes sense to you. Or in case if you have any doubt, then feel free to write down in a chat. Okay, yes, sure. Okay. Space complexity is also O of h. Okay, sorry, I forget to discuss the space complexity. So the space complexity is also O of h. O of h, because of the recursive call stack that has been used in the recursive call. Okay, Piyush, thank you so much. Okay, for the recursive stack space. Yes, Rishit, you are right. So let me just share this code to you. Guys, please hit the like button. Okay, nice work. Thanks, Rika. Okay, so thank you everyone for joining the session.